So thank you for this opportunity. I'm going to present my master's degree work, which is video temporal super-resolution. And here are all the people. We presented this work in ECCV 2020. And this is a joint work with Eyal Naor, George Pisha, Shai Bagon, and Michal Irani. So please feel free to ask any questions during the talk. I want it to be clear. I want you to understand what's going on. So please, if you have any questions, don't hesitate. So I'm going to start with talking about the difference between temporal super-resolution and temporal interpolation. In both cases, we want to increase the frame rate of the input video. However, these two tasks are different. In temporal super-resolution, we also want to recover dynamic events that occur faster than the frame rate, hence are invisible in the input video. This includes undoing motion-aliasing and motion blur, which I'm going to explain these two phenomena. So when we have a higher temporal resolution, it means that we have a higher frame rate video, like we took it with a faster high-speed camera. We want to recover the events that occur faster than the frame rate of the camera. So let's look at this example. This is an example of motion aliasing. The fan is rotating clockwise faster and faster, and at some point it begins to seem to rotate counterclockwise. This is because the frame rate of the video is too low. So this is motion aliasing. The other effect we talk about is motion blur. From the moment the shutter of the camera opens until it closes back, the fan moves. If it moves fast enough, it induces motion blur. Note that these two effects cannot be removed by any means of temporal interpolation, no matter how sophisticated they are. The temporal interpolation cannot produce new information that does not exist in the original video, in the input video. In contrast, we want to do temporal super-resolution. It aims to resolve both of these effects when it upsamples the video, the frame rate of the video. Any questions about temporal super-resolution and temporal interpolation? Okay. So let's talk about prior work. When I say prior work, it means prior to when we published this paper. So I know there were some new things from there, but I'm going to present only the prior to our work. So the state-of-the-art temporal interpolation methods were SEPCONV, NVIDIA SLOMO, and DANE, which we compare to. And the temporal super-resolution methods were what we call flawless from CVPR 2019, and a patch-based video super-resolution. Except for the last work here, for the bottom one, all of the top methods are external methods. When I say external, I mean that it trains on an external data set that contains a lot of higher resolution, low resolution video examples. And the last method is an internal method. Like our method, it uses only the input video itself, a single video, meaning it doesn't use any data set of high resolution, low resolution pairs to train from. In this work, we extend the deep internal learning concept to video data. Those of you who are not familiar with this term, I'm going to explain it later, soon. We perform unsupervised zero-shot temporal super-resolution, and we also observe a new type of data recurrence that we did not know before, which is across video dimensions, which I'm going to explain, of course. And all of these allow us to resolve both motion blur and motion aliasing better than the external methods. So what we're doing in this work is we prefer temporal super-resolution by training a convolutional neural network on internal examples that are extracted directly from the input video itself. So a variety of useful augmentations are described in the paper, but I'm going to talk about two main and important kinds of augmentations that we use. One very useful augmentation is obtained by taking coarser and coarser temporal scales of the input video, which we create by blurring and subsampling in time. So this is our video volume. If we blur it and subsample in time, okay. If we blur it and subsample in time, we can find that the fan rotates, faster, and it induces more motion blur and motion aliasing as we go and blur it more. We can also see that we find neighbors. Wait, sorry, it wasn't the slide I was planning for, so one moment.
No worries, take your time.
Yeah. So if we have this original input video and we have the coarser scales of it, but now we know that we can find nearest neighbors in the same, when I say nearest neighbors, I mean that patches of 3 by 3 by 3 or 5 by 5 by 3 have similar patches within the same video volume that we have. But we know that from Shachar et al. 2011 that we also have nearest neighbors in other scales of the video in coarser temporal scales. So what we can do is we can use the fact that we have a lower a patch. The orange patch here is similar to the green one here. So we know how to how this orange patch was created. We took this big orange patch and downscaled it to this one. And if those are similar, we can deduce how to super resolve the green patch. This is what Shachar et al. Done in 2011. It's not a deep learning method. It's an example-based super resolution in time.
Can we repeat the explanation from the beginning again? Well, I'm not sure I understood.
Yeah. So we have we know that we can find nearest neighbors for our patches in our input video in coarser temporal scales. For example, the green patch is really similar to this orange patch, while this orange video volume is a downscaled version in time of our original video. Since this video is downscaled, we know who his parent is. I mean, we know which patch we needed to blur and subsample in order to get this orange small patch.
Mm-hmm.
Since this small orange patch is really similar to this green one, we can deduce how to enlarge it back to the super resolved version of it.
But the green one is part of the first resolution across time, yeah. Or?
Yeah, the green one is inside the original input video.
So, and we want to go further up. Okay, yeah. We want to bring a higher resolution that doesn't exist. And what is that left part with the yellow and is it a magenta? Is it called cube? What is this about? Yeah.
These are nearest neighbors that we know that are in the same scale. We have also nearest neighbors in the same input video scale. So these are also examples for super resolution in time, but we wanted to show that we also have across scales examples.
But this is the same scale. That's not across scale. Within scale, no?
Yeah, it was before. We also have examples within scale.
Yeah, within scale.
And cross
okay.
Scale.
And what do we do with the within scale nearest neighbor calculation?
This is a part of the example-based super resolution that I used in 2011. So we talk about which kind of patch recurrence you have in your data. You have within scales patch recurrence, you have a cross-scaled patch recurrence. And in this work, I'm going to present another kind of patch recurrence that we have, a new one that is across dimensions as well.
Okay, just to understand, why do we need the within scale patch recurrence? What is it helping us with?
It doesn't help you now for the super resolution that I'm talking about.
Okay.
Okay. It's just what you have in the video.
Okay.
It does help you when you think about the entropy of the patches that you need to learn, which is not really large. It's not like every pattern is every patch is really unique. You have a smaller dimension that you could have in a video, but it doesn't like that you find from this example the super resolved patch.
And the entropy within a scale, what does it help us with? Like, well, if we can learn it?
It makes the problem more solvable. If you have some prior knowledge or if you can take the dimension of all the possibilities it can be in a video of let's say 100 frames, which are 1,000 by 1,000 pixels each, it's really, really, really extensive. But if you know that you have some patch recurrence and you have some restrictions that are induced by the fact that this video is a natural video and not just white noise, it makes this problem something you can actually solve. Because if you want to do super resolution, you need to have some prior over your data.
Okay. I'm not sure I'm following fully, but if it's a bit less in the focus, so we can continue.
Okay, I think we should, because it's not really something I'm going to touch in it. Okay.
One question just about the blurring is blurring is across several frames. How the blurring is done?
So here the blurring is done by averaging every 2 frames. You just average the pixel value of every 2 frames and subsample.
Okay, nice.
Okay. So what we can do is we can try we can train a video-specific convolutional neural network on these examples. What we were going to do is not use the patch-based traditional, let's say, not a deep learning algorithm. We want to train a network on these examples to learn how to resolve the motion blur and aliasing, wants to undo it. And once the network is trained, we can train a network to learn how to recover this original video from this downscaled video, and we can apply the network again on the original video to get the higher resolution video. And I think I'm gonna pause for a minute because I think it's not the, I'm sorry. I just want to see if I have the right slides that I wanted. Yeah, okay, it's fine. Sorry. So, yeah.
Sorry, can reference?
Yeah. What? I'm not hearing you well.
If you can repeat the difference in the inference in your method.
The difference in my method?
Yeah, but
I've not presented the method yet. Okay, I'm getting there.
Maybe if you could write down, Patel, maybe if you could write down the question and the chat will take it for you.
So let's make it more clear. we're training a video-specific network to increase the temporal resolution from a single video. We have only the video itself to learn from, so we perform some augmentations on the data. And I'm going to present two kinds of important augmentations that we're using. One is the temporal downscale, which we do by blurring and subsampling. This is what I explained here. And this augmentation was done also in Shachar et al. Work in CVPR 2011, where they used it in a patch-based super-resolution method. So we're using it as examples to train our network. Another kind of augmentations that we do is cross dimensions. And that's what I'm going to show now and explain what it means. We observed that patches also recurred across dimensions. What does it mean? Okay, so for example, if we have our video volume, X, Y, and T, what we call frames are slices at a specific time of the video volume. Okay, but we can take the same video and rotate it so that the spatial axis becomes like the temporal axis. Now, these slices is what we called spatial slices, because they are, for example, here, YT slices at a specific X. They contain one dimension, which is temporal. This dimension here, the temporal dimension, contains temporal aliasing, which we want to recover, which we want to undo. So this is what we called temporal slices, and these are what we call spatial slices, which are the frames. And please note that the patches here, if you can see here, the patches of the cheetah looks really similar to the original frames. They bear similarity to them, but they contain aliasing. So what we can do is we can use the spatial slices and that they provide us the high resolution examples we need in order to increase the resolution in the t-axis. And increasing the resolution in the t-axis is actually doing temporal super-resolution. Okay, so the spatial axis teaches us how to undo the aliasing in our video. Questions? All right, let's look at a video of how these spatial temporal slices are formed. If we have a fast video of the cheetah, as time goes on, we can see the temporal slices form. This cheetah video was recorded at extremely high frame rate. The top right is the YT slice of the video, and the bottom left shows the XT slice of the video. But notice the strong similarity we have between patches in the top YT video and the slices in the original video, in the frames. Now we're going to look at the same video, but in a lower temporal resolution. In a lower temporal resolution. Now it's, if we play it in 1/8 of the original resolution, not only does the video run really fast, but also because we have less frames, but we have the temporal axis is aliased now. It's squeezed and it contains less information and it has aliasing. So lots of the temporal aliasing is contained in, we can resolve it by using the spatial frames. And we use them as training examples of how to increase the temporal resolution. So how strong actually is this recurrence? We wanted to see if it's just the cheetah case that we can see it, if it's just a visual effect, or does it really occur strongly in the video? So we found that many patches found their best match across dimensions. We took the cheetah video, and for each spatial slice, we looked for the 10 nearest neighbors it has, both within the same dimension and across dimensions. And here on the right, we can see a color coding of how many of these 10 nearest neighbors actually occurred across dimensions. So the red shows that when it's red, it shows that all of them, all the 10 are across dimensions, and when it's blue, none of them, and all the in-betweens. So we can see that most of the patches find their 10 or most of their nearest neighbors across dimensions, which was very surprising for us at first. But it is something that we can use. Any questions?
Are the nearest neighbors just nearest neighbors of the pixels, or is it some machine learning model?
So this test is not a machine learning model. It's just the nearest neighbors of a patch of 5 by 5.
Okay, that answers my question.
So we can use this knowledge to train our network. Why does it happen? Why do we have cross-dimension patch recurrence? So let's look at the 1D illustration of an object moving to the right. As it moves to the right, we can look at our video volume over here. The object is moving to the right. And here we take a snapshot of it at each time. If we take the temporal slice at some specific x, we get an identical, it is identical to the original object. This happens because the speed of the motion is equal to the frame rate. But now if we take demonstrate a lower frame rate camera, let's say take only other 2 frames. If we take the temporal slice at a specific x now, we get an aliased version of our object. And this is the temporal video that we want to increase its resolution. And we want to get from here to here. You don't see my mouse. We want to get from this motion aliased version of the object to the original one, which we don't have. But we do have the original object in the spatial dimension. So we can use this example in order, to learn how to increase the temporal resolution. We can take this object, downscale it, and learn how to recover it. And this will allow the network to learn how to recover the same thing in the t-axis. So please note that it doesn't matter how many external videos I would learn from. If I have like an infinite database with lots of videos with high resolution, low resolution examples, this information is very video specific. No matter how many videos I will take, it will not let me know that between a blue and a yellow dot should be a brown dot. This information is specifically unique for this video, and this is where we get the strength of learning from internal examples. Okay, so I'm going to present quickly the Zero-Shot Super-Resolution deep internal learning that was presented in ZSSR by Shocher et al. CVPR 2017. This is a work done to increase to perform super resolution of images also by internal learning. So what we did is expanded it to temporal super resolution for videos. So the ZSSR takes an image, downscale it, and train a network to recover the original resolution. It also performs some augmentations, and then the same network, which is fully convolutional, means you can apply it to any size of input. They take the original image, forward it in the network to get the higher resolution super resolved image. And yes, they perform some augmentations to train the network in order to achieve that. What we do here in our work, we take a video, we downscale it temporally. The convolutions are now 3D and also the output, but the strength and the core of the work is in the augmentations that we choose to perform to the training dataset that we create. Our augmentations are both within the same scale, meaning mirroring rotations, but across space-time scales and across dimensions, as I mentioned before. So this is the major difference between the works. Any questions?
I am posting now on the chat Asaf's talk in our community about deep internal learning for anybody who wants to dive in a bit deeper into this subject. It'll be also on the recording page after.
Great, thanks. Okay, so now we're going to talk about how we create a training set from our single video. We want to train our network. We need to create some training set, some training example from a single video. So we have this input video, and we also have a Coarse-to-Temporal scales. We can take it and blur it and subsample it to get Coarse-to-Temporal scales. The Coarse scales are examples that have more speed, more motion blur, and more motion aliasing than the input video. What we also do is create spatial scales of the video. We get this way videos that are with less motion blur and with a slower motion. What was a motion across 10 pixels is now a motion across 5 pixels. So that way we have less blur and less motion examples. We also create all the in-betweens, all these scales. And an important point is that when we downscale both spatially and temporally by the same rate, we get examples here that are with the same motion blur and the same speed as in the original video. And this will be important for our last slide, I think. So all of these examples are within the same scale of within the same dimension of the original video. Let's put them aside. These examples are same dimension, and we also have the cross dimensions examples, which are what we talked about before. Now, if you have this input frame with a high temporal resolution, where the x is plane as if it was a temporal axis, we can downscale it in across this dimension, x dimension, to create a low temporal resolution example and train to recover the high temporal resolution frame. Then, when we have the YT slices, we want to increase the t-axis. Since these are similar, we can use it to obtain our high resolution t-axis. So this is an important point. If you have any questions about that, please let me know. No questions means usually that something wasn't clear.
There is a part that's not clear, but I don't know if we should go back to it. It's that part that says that if you look at the slice of YX, it also interpolates into the slice YT because it's similar feature structure on the visual side. For me, it wasn't fully clear, but maybe it's my.
Can you repeat? You mean that?
Yeah. Interpolating from YX to YT is okay. Why? So I think we explained this like 3 slides ago when we showed the aliasing and how across a temporal scale it doesn't happen, and when you have T as the x-axis, it does happen. It wasn't fully clear to me, but maybe it's just me because
this is a property of the natural videos that we found, that we have patch recurrence across dimensions. So lots of patches here are very similar to patches here.
Yeah.
So you mean why it happens, or
yes,
that the fact that it does? Why it happens?
Yeah.
Okay, so we can go back to that slide and this one, I guess, right? When you take a video, you look at some point in when you look at okay, let's start from the beginning. If you move, this is like a 2D version, so we can visualize it. Or for 1D object, it moves. You can see that if its speed matches the frame rate, then you get that the temporal slice, which is the vertical here, is really similar, is identical to the horizontal object that we have here in X. It happens because as objects move, they cross a specific location in space. So it's true that that speed does not always match the frame rate, but since we have lots of other augmentations that increase and reduce the speed, at some point you will find an example that matches your motion, and it will get you can learn from it.
What are types of augmentations you said that reduce the speed? And that I don't understand.
What? Why does
this last sentence I couldn't understand. You said we have some augmentations that reduce the speed, which allows for the object movement to synchronize with the speed of the camera. I didn't understand.
Yeah, because if you have this, if I downscale the video spatially, I have an example of the video which is in lower speed than the original one. So maybe the cross dimension example for a specific motion, it will not be found in the original video, but in some specially downscaled video version of the video. Maybe there, when I perform the cross dimensions, it founds the example that it needs. So that's why we need a variety of motions in the video. That's why we downscale both temporally, spatially, and cross dimensions to get a variety of speeds of motions and everything that we need.
This example is good for translation motion, right? So what happens if you have affine motion? Do you still have the same property?
So yes, the answer is yes, because we have the patches are really small. They're 5 by 5 by 3. So you can think about it as a momentary
translation.
That's a local motion, right? Mm-hmm. So for that, for 3 frames, it's relatively close to a translation.
Okay.
Okay. More questions?
3D motion, probably. I mean, camera getting farther or closer. How would that affect it?
So it's the same answer as I said before, because if you look at 3 frames, it's approximately something that you can linearize, right? So we look at really, really small frames in time. So we don't try to model a large motion across many frames. Just for 3 frames, it's relatively linear.
But getting closer and farther is actually, I think it breaks this linearity assumption because, you know, a patch is, you have multiple directions of motions.
Yes, but locally on a 5 pixels by 5 pixels by 3 frames patch, it's quite similar. You don't look at the whole image. You look at the small patch in the volume.
Okay, I'm not sure about that.
Okay. Let's go back. Any more questions about this slide? So I think the main thing here is that the cross dimensions allow us to use the higher resolution that we have, especially to increase the resolution in the temporal dimension. And we can do that because there is a similarity between the temporal axis, the temporal patches, and the spatial patches. So how our network actually looks like. We use a simple 3D fully convolutional network. We of course need it to be fully convolutional because we train and on a variety of input sizes, and we inference on another size of the video, of course. So this is our input video. We perform cubic temporal interpolation, which is not a really smart interpolation. And we learn the residual from that interpolation by using 3 by 3 by 3 convolutional layers and 5 1 by 3 by 3 convolutional layers. And this is our output. So it's only 8 layers. We learn the residual, and the training takes around 2 hours, and inference is 1.7 seconds per frame. Yeah, so the upside here is that the training is not really long. The downside is that we need to train on our video specifically on our input video. So if you have a new video, you have to train again. That's what happens when you do it video specific. And
where can we read about the cubic temporal interpolation? Just understand a bit more better what it is.
I think it appears in a lot of places. I think it's really not a really complex concept, since it performs cubic interpolation across the t-axis.
What does it mean?
That you use more than two frames to perform, like linear interpolation would average every 2 frames, and cubic will use more of the frames in some polynomial way to interpolate the in-between.
What frames and what polynomial, like these details, where can we, like, is there like maybe a link or a paper or an article to read about it? Or because I was trying to search online, it was a bit tricky. I thought maybe.
Really? I thought Wikipedia will have something really basic for that.
It doesn't look like there is. Yeah.
So maybe in
for interpolation there is. But
I think there is a cubic interpolation, and you need to search cubic interpolation.
Yeah.
Just apply it to all dimension.
Yeah, exactly. It's just cubic interpolation. The temporal means that it performs on the temporal axis, but it's just 1D temporal 1D cubic interpolation. And if I can look for it after the talk, but I think you will probably find the implementation in Python or something, and there you will see the.
Yeah, if there is something. This is also okay. If you can share us after the talk, it's fine.
Okay, so the whole thing I talked about, we do it in a coarse-to-fine scheme. We don't train our network on our actual input video, on the big one. we first downscale it spatially to get a small version of it. So when it says here S1 T1, it means that S is 1 times the original spatial resolution and 1 time the original temporal resolution, T1. So we start by downscaling it spatially to S1/4, which is 1/4 of the original spatial resolution and the same temporal resolution. Here, the motion is smaller and it's easier to learn. It's also less pixels and the volume is smaller, so it's easier to train the network with, but also we have less blur. And
Question, how do you do the spatial down resolution?
A simple downscale.
But what kernel do you use?
I think it's a
you can use a lot of things. You can use a lot of kernels to do the downscaling.
Yeah, I think it's the cubic kernel, not something very sophisticated.
I think we talked about these also in a soft talk about deep internal learning, if I remember correctly. And also
but in a soft talk in deep internal learning, the spatial downscale is really important to match the. In his work, it's really important in which kernel you downscale the image, and he has this method of looking for the right kernel to downscale with. But here we don't do that. We just use a simple cubic interpolation downscaling. No special method for that, because the need is different here. Okay. So here it's like a stupid interpolation. And we train our network here to increase the temporal resolution by a factor of 2. So after this network here, we get S1/4 and T 2 times the original video. And what we do now is we want to recover the spatial resolution by a factor of 2. We want to go from S1/4 to S1/2, and we do that by back projection. So back projection is when we take the S1/4 T2 and we use bicubic interpolation to start with some S1/2 video, higher spatial resolution video, and we solve a set of linear equations that requires two things. One, that if we downscale this video back, it gives us the network's output. And the other demand is we temporally downscale this video, we'll get the original video, the original temporal resolution of the video in S1/2, in half the spatial resolution of it. So it's just a linear, a set of linear equations that we solve iteratively, and we get this S1/2 to T2 video, which means it's half the original resolution in space and twice the original resolution in time. So this is this back projection block. It allows us to increase back the spatial resolution. Now, what we have here is S1/2 T2, and our network was trained on S1/4 T1. Please note that both the spatial and the temporal resolution here are twice as large as the video the network trained on. This means that they have the same motion, the same speed of motion, and the same blur and the same properties as the original video that we trained on. I mean this small one. So what we do here is we just apply the network again to get a higher temporal resolution. We can do that because we have a patch similarity between those two videos, since they have the same factor in space and time. We use again back projection to get this S1 T4 and apply the network again with the same reasoning to get our wanted output, which is in the same spatial resolution as the input video, but in an 8 times higher temporal resolution. Now it's a good time for questions, if you have.
Yeah, about TSR X2, just to understand how we can train it to know with a 2 times higher frame rate, if you could repeat.
How do we trade it here?
Yeah, how do we train it here? How do we get this data set with 2 times higher frame rate?
We don't train it here, we just apply it here. We train only on the lowest level, and we use the fact that these levels of the have patch similarity to apply it again and again here.
That I understood. This is, I'm sorry about the noise. These are howler monkeys.
Wow.
So I meant the first training
here.
Yeah, how is it trained? How do we get that right side to train for? Or maybe I missed something.
That right side is the output of the network.
But
sorry, I'm probably
you gotta have it for training.
What?
Yeah, the output is usually in the training set, right? Or
no,
in this case, it's not.
No, okay. So when you do your internal learning, you don't have it's unsupervised. You don't have that output to learn to. You use this, you downscale this video in all the augmentations I showed before to learn how to increase this video by a factor of 2. So you perform all the within scale, across dimensions, all the augmentations that we talked about before, in order to train your network how to increase the temporal resolution of this small video. Then you apply it to this video to get a higher temporal resolution.
But the augmentations were not along the time axis; they were along the spatial axis. No.
No, the augmentations were.
So that maybe I missed. Okay.
Okay, I can go back to the how do we create a data set. Yeah. So here we have augmentations across temporal scales, across spatial scales. I think the best way to show it would be actually this slide. We have the original input video and we temporarily downscale it, and we train our network to get the original video. Now this video is applied to the network to get a higher temporal resolution version of itself. Okay, so we have, this is, for example, the S quarter T1.
Yeah, so it was pre-trained with downscaling the times.
Yeah.
Yeah.
With all the other augmentations.
I understood. So actually what I was missing in the last diagram, I was missing one thing in the last diagram, which was from T1, we go to half a T, we train that, we go to quarter T, we train that, and then we have the TSR to switch from T1 to T2, right? That TSR X2 below is actually trained on S quarter, T half. Yeah.
You have T half, you have T quarter, you have lots of mixtures of that, but this is your input video and you perform your internal learning algorithm on it.
That now I understand.
Yeah. The way that you do it is by creating these augmentations across space and time. Okay. So then we get our super resolved by 8 temporal version. So one of our challenges was to create a challenging data set. Our method is good for extreme cases of high motion aliasing, high motion blur. We wanted a challenging data set. So we took high quality videos that were taken with a high frame rate camera that has complex dynamic scenes. And we blurred and subsampled them in time to simulate a severe motion blur and motion aliasing, because in order to test ourselves, we need some ground truth. And we compare the results with the original videos. And you can see here the PSNR, SSIM, and perceptual loss of our results compared to the other methods. Only Flawless actually do temporal super-resolution and not temporal interpolation. So you will see that in the visual examples, you will see that they are the ones that look better than the other methods. But here we can see that if we look at really challenging videos in our data set that have complex things like splashing water and fire and stuff like that, you can see that our method is really better in these videos. Generally, since we downscale the video spatially, we lose the background information, which is better if you don't do that. Okay, so going back spatially is fine. We do that, use back projection, it's fine, but it's not perfect. It's not as maintained as using the original spatial resolution that you have. So even in videos that we can see that the numbers, the PSNR and SSIM, they might be lower in our results. You can see that in the places where you have motion, it looks better, and in the places that are static in the background, it's not better. So we think that combining somehow the two methods, the external method of using the data sets with lots of videos, high resolution, low resolution examples, to combine that for the static areas, and our internal learning method for the dynamic complex areas would be the best way to perform temporal super-resolution. So maybe I will show you the results and then you'll convince. So let's see some results on temporal super-resolution. This is the fan that we saw on one of the first slides. And so here is the top left is the input, bottom left is our results. You can see that none of the other methods can handle this motion aliasing. So it's a very severe motion aliasing that you have here. And yeah, as the fan goes faster and faster, you can see that the other methods have more trouble to recovering the correct motion. And okay, here's another example. This is a real video that we took of a rotating disk. Top left is the input and bottom left is our result. It's not perfect, but it resolves most of the motion blur and aliasing, while the other methods fail to do so. But it's not good only for rotating things. Let's look at the hula hoop example. Top left is the input, bottom left is our result, and bottom right is the ground truth. So I think even in this video, our PSNR results are worse than the flawless result. But you can see, if I pause this video here, you can see how they cannot recover this hula hoop, and we recover it better. And we believe that combining the background from external methods and the dynamic scenes for our method will be the best way. Okay, so let's look at some more examples. Top left is the input, bottom left is our results, and bottom right is the ground truth. Let me know if you want to pause it some way. Oh. Okay, so I wanted to pause right here. No? Guess you can see that here the ball is in two parts. Okay, some more examples. You can look at the feet. So note the leftmost edge of the flame here. And yeah, we applied the methods on 25 different challenging videos, and you can find the entire data set on our website in our project page, and you can find the code as well. And feel free to ask any questions. And thank you for listening.
Thank you. Looking now on the YouTube. No questions there.
Can I ask a question?
Of course.
Yeah, so any thoughts about how to make it work faster? I mean, like meta learning, maybe for, you know, for single shots, I mean, zero shot, but by meta learning, you can reduce the time to converge or something like that.
Yeah, so we thought about that training, how to make it train faster. I'm not sure we went to the meta learning direction, but it could be interesting. And well, actually we didn't try these methods because we had to present something at a schedule, but it is something that we thought about how to make it faster. And as I said before, I think combining both external and internal and somehow starting from a better starting point for our network will be best. So yeah, there are many directions that we can take it through, but well, I did not continue that work from there.
Why did you use?
What's the training?
Sorry. Why did you use back projection for spatial upsampling? I mean, can't you use just the ZSSR methods, frame by frame?
Yeah, we could, but we wanted something simple, fast and simple. You could do that. Probably would be better. We just didn't want it to make it any longer, although ZSSR is not really long, but for technical reasons, it was easier for us to do it. Okay. But it's a good idea to actually use that.
Regarding the training times, what were they really on? What long of a video, what resolution, and what hardware?
So the resolution was, let me go back, around the 1028, I think. Yeah, 1280 over 720 over 3. The hardware was V100 GPU. And another question, I think around color and
1.7 seconds frame.
Yeah. And this we took around 100 frames tops. We can do this super resolution even on shorter videos, on like 20-30 frames. You can actually, that's enough. But 100-200 frames is top mod that we used.
And again, what was the training time? I don't think I heard.
2 hours training.
2 hours on 100 frames on a 1200 by 700 pixels. Okay, on V100. Wow.
Yeah. Yeah.
Tough.
Yeah.
Yeah. I think we had a question by Aditya. If you don't mind, could you please explain the difference in the results of spatial and temporal downscaling?
The results, can you repeat, please?
Yeah, it's in the chat. If you don't mind, could you please explain the difference in the results of spatial and temporal downscaling?
Okay, so when you take a video and you downscale it spatially, you get a video which is which its motions are smaller. Like you have the motion, we have less speed and less motion blur, because if you have a blur across 20 pixels, now that you downscaled it by 4, you have the same blur over 5 pixels. So we have sharper frames, and the speed is smaller. If you have some motion across 10 pixels, now it's across 5 pixels or less, depending on how much you downscale this video spatially. When you downscale it temporally, if you had a motion that took 4 frames to pass 20 pixels, now each 2 frames are squeezed to 1. So the same motion of 20 pixels is now across 2 frames, this same 20 pixels. So the motion is faster. So we have more blur and more faster motion. So these examples are more blurred than the original video, and these examples are sharper. And when you do them both in the same scale, that you get the same blur and the same speed. Does this answer your question?
Yeah, it does. Thank you.
Thanks.
Any other questions, anybody?
Just a thought, if we do like a quantization or let's say the repainting of the image after taking it to, I don't know, reducing the resolution to black and white, I mean, the quantization or whatever, do you think it will hurt badly the results, or you think it could be like a shortcut to enhance the speed?
Well, we actually used int16, not really harsh quantization, but we didn't see a significant difference when using int16. Black and white, if I have to guess, I would say it wouldn't harm the results much, but you will have to recover the color, of course. So depending on how well you do that. You're looking for a way to train faster?
Most of it, yes.
Yeah. That's the big issue, right? I think that the fact that we use here the cubic temporal interpolation and learn the residual from it and not from a smarter starting point makes the training slower. And if we would use some other method to get an initial temporal interpolation for our video, maybe we thought about using one of the external methods as a starting point for our temporal interpolation and learn from it, maybe that will be a better way, and maybe that will train faster.
Thanks.
So if no more question, we will wrap it up. Liad, would you like to say something, or should I?
Oh, I have a small question.
Yeah.
You presented 2 methods to build the training frames. One which is shorter in time, and one which is blur.
Yeah.
Is there any significant to blur versus size? Or
You mean
other
the
one?
temporal downscale and the spatial downscale?
Yeah.
It gives different kind of examples. You have examples that are with a lower spatial resolution and lower temporal resolution on all the combination of them. And when you use the both types of examples, you get a richer example bank that the higher.
I'm sorry about that, everybody. I think.
What?
I'm sorry. I think my internet crashed for a second there. I missed something. Maybe. Go ahead. Sorry.
Okay.
So when you use
yeah, I thought maybe the bluer has more significant than the size, just in intuition.
Well, you actually need them both because you want to find the best nearest neighbor to learn how to increase the temporal resolution from, and you need to have a large variety of patches to learn from. So each patch will have its best friend that you will learn from it. If you use only one type of interpolation of augmentation, you will not have a rich enough data set for your learning. So you need both, and it applies also to different motion sizes.
Okay, and just another question. Just what is the footprint, the memory footprint required for this kind of algorithm? If you touch that aspects, these aspects.
You mean how much does it take from the GPU?
Yeah,
or,
from the memory point of view.
I don't remember. It really depends on the size of the video. Like if you take 100 frames or 20 frames, it's really.
Okay.
I think around. Well, I don't remember. It's been 2 years. Sorry.
Okay. Thank you.
From the GPU memory, it takes, I think, 6 to 8 gigs, but the memory, I don't remember.
Okay, thank you.
Thank you, Liad.
Anyone else?
Wonderful lecture, and thanks for the patience.
Thank you.
For sure. Thank you, Liad. Maybe we'll wrap it up really. Liad, thank you for the patience and for re-explaining and re-explaining.
Of course.
It was very nice having you over. Everybody, also thank you for joining as usual. Our next talk is in 3 days, so maybe I'll see a couple of more names soon again. And until next time, I will say bye for now for everybody.
Thank you for listening.
Thanks a lot. Bye-bye.
Thank you for the presentation. Bye.
Bye-bye.
Bye-bye.